What's up? Where are we at?
Can we do number 3, 4.2? So pretty much use the reduction method. So y equals y1 u, and then
Yeah, so real quick, this is kind of nice. This will be a nice little review, plus I'll look at the problem. Why do we do, so in 4.2, they tell us one of the answers, and I said it's kind of, 4.1 is especially frustrating because it's just definitions and we don't get to solve anything. 4.2, we sort of get to solve, but they give us a solution. That's still a little frustrating. Why, if they give us a solution, why do we say that, why is this something we can do?
because it's non-linear, so it's a ratio. There's another, we know that there's another y, in a sense, right? Because there's a second derivative. So there's
What is the key phrase?
Second order.
Okay, sure, it's second order, okay. But to be honest, we could actually do this this process on other things.
Higher order.
True, but what is the key thing about any two solutions to a second order DE homogeneous? They have to be independent. They have to be linearly independent, which means what about their ratio? Their ratio can't be just a constant. It can't be a constant. That would be kind of the definition of dependent, right? So that's why doing this makes sense. Right? Otherwise you just say, why are we allowed to just go u times, why would that be true? Because their ratio has to be a function of x. It can't be a constant. Okay, cool. I like that. That's what makes this whole thing work. So number 3, did you have a specific?
Yeah, so last lecture you showed us the second part first, and then you showed us the first part. My question is kind of like, how do you like put those two together in a way? Like I'm having a problem. I can take y prime. I can find y double prime and stuff, and then I can plug everything in and reduce. Then what do? I guess is my question. You said u prime equal to w then after you.
So anytime, and yeah, exactly, good. Okay, that's what you meant. So the first thing we did was look at the general idea of if I had something like this, is there something special about this? Yes. And we talked about if you take a derivative, you make its own function in its own right. So then you can kind of substitute here. This one we would substitute u equals to y prime, and then u prime. So now I'm kind of like, that's where the reduction of order sort of comes in. I've gone from a second to a first because I treated the first derivative of y as its own function, which it is. So the relative relationship between these two are remaining the same, but overall I've reduced the order.
Right. For this one, so y equals u y1. So taking the first derivative, you'd have to take the product rule.
So y, in this case specifically, y would equal u times cosine 4x. I like it.
Right.
Yeah, so then the first derivative, you'd have to use...
Here's what I ended up with. Maybe I can make it simpler. So I ended up with u double prime cosine of 4x minus 8 u prime sine of 4x equals to 0.
All right, let's do this. Let's do this. If you guys haven't done this problem yet, go ahead and try to do the next few steps. So even if you weren't here the other day, this is the substitution we're going to make, which means I need to figure out what y double prime is so I can place that in here. So I'm kind of transforming this into a something involving u and x instead of y and x.
Is it cosine 4x?
Say again?
Is it cosine 4x or?
Yeah. Cosine 4x. Mm-hmm. Yeah.
Are we treating u as a variable or constant?
So u, if I want it to be really, really specific, y of x equals u of x, y1 of x. Because again, what is u fundamentally? It's that reason it's not dependent.
The ratio of the function over.
If the second and the first were dependent, then they would equal a constant. But I don't want to let them be dependent. I can't, because otherwise I wouldn't really find a truly second solution. So that means that the ratio must be some function of x. But in the interest of time, I can sort of drop that x off, and we know that u is a function of x because of what it's supposed to do. Okay, so yeah, when you take the derivative, you do need product rule. So what would you guys get here? U prime.
Cosine 4x
Sure.
minus 4u.
I like some minus
4u.
4u sine 4x. So then a second derivative. Derivatives should be your bread and butter, right? You should know. It should be like, oh, thank gosh, just derivatives right now. Yeah.
And there's like no chain rule or anything associated with u. Take the derivative. You just did u to u prime.
Yeah, see, it's a function of x. So the inside function is x. Yeah. It's not a function of like square root of natural log of x or something. It's a function of x, thank God. So when you take the second derivative, double prime, that part's always nice. That's easy.
Minus
Yeah.
4.
You basically get this again with the prime, minus 4 u prime sine 4x, and now you attack this dude.
Minus 4u.
Yep, minus 4u prime sine 4x.
Minus 4u.
U minus 16. Yeah, cosine thing. I like it. And it's negative, of course, because that minus sign applies to both results from that product rule. So far, so good. So in a way, this, like I said when we first went over this, it feels a little bit like the verify problems, because we're just taking derivatives and throwing it back in there. But when you throw it back in there, you're not really done. It actually becomes another form of a DE that we still have to solve. What's going to happen a lot of the time is it's going to become linear. And then you have to use an integrating factor. But sometimes, like the problem we saw the other day, everything went away except the second derivative, and then it can kind of attack that directly. So what happens here when I replace y double prime, and is there anything, obviously here I could put together, yeah. So u double prime cosine 4x minus 8u prime sine 4x, 16u cosine 4x.
Plus 16 cosine 4x. The 16 right there.
Oh yeah, you know, this is y double prime. So now we get u double prime cosine 4x minus 8u prime sine 4x minus 16u cosine 4x plus 16u cosine 4x, because that's what y is. So that's pretty much guaranteed to happen if you do this correctly.
So here you introduce a w, right?
Yeah, let's take a look. Let's take a look what we got. We got u double prime cosine 4x minus 8u prime sine 4x equals 0. So you do have no u term. So in one sense, we got into a higher order differential equation. We said, how do we solve these things? Well, let's do this. And then we get to this point, and it's still a higher order. And then party should be like, oh, good job. But the nice thing is, if that's a function in its own right. If we call it w, then this is w prime. So then we've reduced it to first order. We've reduced it to first order, and now we could use the methods we know from that. So yeah, so is everybody decent with that? That feels a little bit like you're cheating, but I desperately want you to realize you're not. When you take a derivative of a function, you've created a new function. Let me call that new function w. Now, what did I do to u prime to get u double prime? What's the relation? I took a derivative. So if I call this W, then I'm going to put what here? W prime. So the relationship between these two are maintained. Right? So if I solve and I get W, then what am I going to have to do with that? I'm going to have to figure out what U really is. Since W is U prime, it's going to involve integration. I like it. Do you see? So you are making it easier to do this, but you're making a few more steps at the end to get back to the actual variable you want, the actual function you want. So here if I say W is U prime, W prime is U double prime. So then I get W prime cosine 4x minus 8W sine 4x equals 0. Yes?
When making W, you probably don't have to attach like the 8 sine 4x, like take the derivative of that whole thing. You just like pull it off, I guess.
No, yes, thank God.
Okay.
I mean, you're just looking at U prime itself.
Okay.
Yeah, you don't want to bring these into play because that would get a little bit worse. Now, does anybody see something about this?
They're separable.
Yeah, they're separable, right? So try to finish that out. This will be a nice little thing about separable. Separable should be, you should wish for separable problems, really. Just make sure everybody sees how this is separable. W prime is in a different notation is what? dw dx. So then I can, what do you get when you separate this? You add that over. Yeah, okay. dw over 8w.
Sine 4x over.
Yeah, sine 4x over cosine 4x, which we can talk about. dx. Yep. I'll take this up here. So we get integral dw over 8w equals integral tangent 4x. Yeah. I don't know if any of you guys have memorized the integral of tangent. You can actually see it, what it's going to be here, because the derivative of cosine is in here. Yes, so it's going to be ln cosine, that 4 is in there, and plus, you got to be careful because, of course, the derivative of cosine is negative sine. So it'll actually end up being negative ln. Yeah, we'll get to that. Cosine 4x. And of course, if you took that derivative, would you get, yeah, exactly. You get that 4 that wants to pop out that you want to kill. And of course, this will be and now I want to show you something. Let me show you the flexibility. See how this over 4? You see how that 8 is really kind of sucky there? I really wish it wasn't there. Well, I could just bring it up there. I could have right here just left the 8 with the sine over the cosine. You guys see that? Because a lot of you guys will probably make that natural log of 8w, which is not quite right. So better leave it there, because then it can just interact with that 4. That's awesome. And here, of course, we get ln W. I'm waiting for the piece, the 180.
Let's see.
Yeah. So then W equals what? How can I do this? Let's see, over here I'll get negative 2 ln. Yeah, so it'll be e to the,
ln cosine 4 to the negative
all right, I like that, ln cosine 4x
2
to the negative 2.
times
Yeah, good, times
c to the 2c.
e to the c. So that could become like a c1 out front. So that's that new piece in this class where you have to keep track of the constants and they have to be affected. Yeah.
You do the ln, one of those just cancel out.
Yes, good, exactly.
Cosine 4x.
Beautiful. So that's the next step. Thank God those go away. Do I need the absolute value? Because it's squared, right? So I get a new constant over, or you could either write it over or you could write it as what? 1 over cosine is secant. So secant squared. All right, let me stop there for a second. Which you really right now should go, oh, thank God. Why? Because what's the next thing I have to do with this? Where the hell did W come from? Yeah, it's U prime. And U itself is going to be what I want to use to get my answer. So it's like I got a couple steps to go back. The dominoes are going to start to fall back over. So if W is U prime, how do I figure out what U is? Integrate. I love it.
Where's your ego in W? Sorry, I wasn't following. Oh, they cancel out, so you're not.
I like it. So now I can do du equals the integral c1 secant squared 4x dx. All right, W is du dx. I like it.
Tangent. U equal tangent.
Yeah, so U, this is an awesome problem. I love it. U equals
C1
c1
tangent
tangent 4x.
plus C2
Divided by 4.
Yeah, divided by 4
plus
plus c2. You guys are all like, this is one problem. Yeah.
And then you just substitute that.
Yeah, so now, and of course this you could just make C3 if you wanted to, right? You see the progression of C's? Oh, I can see the faces already. Really? Yeah. All right. So let's see, U is C3, tangent 4x plus C2. So then what do I do with U to get my answer here? Y equals this stuff times Y1, which was cosine 4x. Oh, yummy. And this is kind of nice because, of course, what's cosine 4x times tangent 4x? Yeah. And then this part is really just picking up, so you are getting the total answer there. And like I warned you guys, especially the online people, it wants the specific new piece without a constant, right? That's what it wants for that kind of problem. It wants to know what the new solution is that you've created. This is the complete solution because it's got the one we know already. So what's the new one? Sine 4x. I like it. Now I would hope that a few of you guys realized that was a long-ass way to go for something you should have already known from the beginning. I mean, this is something we've looked at before to try to figure out by observation what the answer is. All right? So if I say solve this and I don't say using any specific method, dear God, I really would hope you'd go, well, by observation I can tell. Because what's related to its own second derivative?
cosine sine.
Cosine is sine, yeah. Cool. This is a really decent problem since you know what the answer should be to get used to reduction of order, yeah.
How'd you go from tangent to sine right there?
Oh, distributing this cosine. Yeah, I like it. So see how important the C's are. If you forgot that plus C2, you wouldn't have picked up, you wouldn't get the complete solution. I like it. That was a good review. I like that. Anything else from homework stuff?
Yeah. Same 4.213. It's pretty much the same thing, just the derivative is more gross, right?
Okay.
'Cause I
Yeah.
know-
Yeah. In fact, this is good. I wanted to do an example of something that wasn't related to the next section. So I don't know if you guys remember, we did a few problems and I tried to relate it to what's coming down the road in the next section. Maybe you forgot. Okay. Well, we're going to do the next section here in a minute. So everybody got what they want from this? More than you wanted? Okay. Let me look at that here for a second. OCD, it's fine. So we can knock out some of the homework. You guys, it's the same exact process. What number 13 says, this. Oh yeah, this is beautiful. Probably one of the few people in here that would say that. So yeah, I agree with you that derivatives could get.
And I also tried doing the shortcut, but that just got.
Yeah, I haven't even talked about the shortcut yet, so we'll. Some of you guys are looking at it like shortcut. Yeah, read the book. It's crazy. You probably could imagine that I'm somebody that would lean towards making you do the full method, right? But I will definitely talk about the shortcut and allow you to use it when I don't tell you you have to use the full method. But you will have to do the full method at least once on the test. Okay, so how do we do this? Yeah, well, if you divide by x squared, do you need to?
No, you just need to.
Multiply y1 times u, and then go from there.
Yeah, so if we know a solution already, and in fact, you need to go back and figure out what type of DE does this work for. That's another, when you learn a new method, number one, it's got to be homogeneous or homogeneous. I love it. And secondly, what else has to be true?
Second order.
Well, higher order, right? Second order is what we're focusing on right now. Linear, I love it. So it's all of those things, right? So it doesn't matter that it's got functional. In fact, we started off with a2x d squared y dx squared, so forth. So they can totally have these functional coefficients, right? So what's the process? I assume that there exists some y that is.
Sine of natural order x times.
Yeah, so ux sine natural log of x. Yeah, I love it. I can see your faces. Now, of course, this is going to be practical. How many parts does it have?
3.
3. I love it. So it's like FGH, right? F prime GH, F G prime H, F G H prime. And you've got to get Y prime, Y double prime. They're both showing up in there. So let me see. We'll do a few of the first steps here. At least one of these derivatives is nice, right? You got chain rule in there, all the old friends are present. first couple that are nice. Yeah. That's a derivative of the middle dude, just one, I like it.
Plus u times x times negative 1 over x.
Well, ux times cosine
Over
of
X.
ln x divided by
Okay.
x, because that's the chain rule piece. I like it. And of course, in the last one, so it's not quite as evil as it looked. It's still semi-evil, but not completely evil. I can sense the good in it, right? So y prime, just rewrite this real quick. Cosine ln x. And then, of course, the second derivative. And you got 3 parts. One of them has 3 parts, and 2 of the other ones have 2 parts for product rule, right? How you guys doing? You guys all right? Oh boy! If you think this feels like busy work, you don't know what's happening. Don't know. What's most important on a problem like this? I mean, obviously you feel like getting the answer to this specific problem is important, but what's most important is, do you understand the method? Do you know when to use the method? Do you know why the method works? Do you know the steps of the method? I grade that kind of thing much harder than I do, did you get the exact right answer? Now, you'll lose some points if you don't, but not as many as if you show me you don't know how the hell to even do the problem. And this sort of is just a revisiting how do you take derivatives, to be honest. Right, so that's this guy so far. And then you'll have plus u prime x. It's going to happen just like over there. You guys see that? Cosine ln x. Let me just cross do that. Make it a little bit easier. That's this guy, right? That's all his parts. And then you just keep going. Now, once you're there, how do you know you're going to be on the right track? I'm not going to finish this problem out. I'm going to let you. I want to make sure everybody got off on the right track. Does this help you out at all? Okay. I don't want to do the whole problem for you. We've already done one homework problem. But once you plug it in, how do you know you're on the right track? What's going to happen?
They cancel each other out.
Yeah, the only u terms left should be, what u term goes away? The term that has just u in it. I love it. And then you can do that reduction of order thing, that just straight substitution step. I like it. So you guys have very thoughtful looks on your faces. I like that. Just a good face to put on when you're really confused. Look thoughtful. All right. So I do have a little handout that's got a little example of this process for you, but it also has the next section in it. I want to get into that next section. Okay. So how do you guys feel about reduction of order? I think what's the worst part of it is when they give you a rather disgusting first solution. Because like you said, it's going to be disgusting as far as derivatives. But the process itself, you just slog through the derivatives. Do you understand the process? That's what's most important. Okay. Now, I anything else left over from homework before I get back into 4.3? All right. I sort of previewed 4.3 a little bit through careful choice of examples last time. Let's do this. Let's do this. I like this. Here we go. Here we go with the one from this. Okay. Oh, so let's talk about this. So if I have section 4.3, second order, linear, homog, D, Lord. Right? It should be color coded or something. Then it's going to look something like this, possibly. And this is going to be with constant coefficients. So that's why I put A, B, C instead of our normal A2 of X, so forth. Okay. We actually did a few problems like this where I gave you the solution, we did reduction of order, and then I showed you how it seemed to relate to factoring somehow. So let's kind of just attack it directly. Let me look at just a piece of this. If I had y prime plus y equals 0, this is one you should be able to do by inspection. So you need something, a function, who is like terms with its own derivative. I like it. Yeah, and in this case, e to the negative x. That would be a solution, right? And this is first order, homogeneous. So how many answers should it have? 1. I like it. So then y equals c e to the negative x. How do you get the negative? Because, of course, you need a negative 1 to come down so that this ends up canceling with itself. I like it. We've done that kind of thing before. By observation is not always the easiest thing to do. But there are certain things with first derivatives, second derivatives, e's, cosines and sines. Those should start to become a given in a way. Slowly it might, right? Okay, so what we've done now is we've just tacked on one more term. And so now I want something that's kind of like terms with its own first and second derivative. So why should I think it might be anything else than good old e to some power of x, e to some multiple of x? So let's try. Let's assume it is, and let me kind of force you to use the same letters as are normally used. So try y equal to e to the mx. So just take a minute. It's going to be a lot better than that last one with the sine and natural log of x. And you guys use that to substitute into this and see what happens. Now, obviously, I'm hoping you guys start to realize how things come together. You have that fundamental set of solutions idea. If I find that this works, then I'm going to use constants to put them together to be, so it's going to be some constant multiplier. But that's a given. I'm not going to do it for right now. That'll have to be thrown in at the end. What do you get when you put this in there? So y prime, of course, will be what? MEMX, I like it, and y double prime, m squared E. So when you throw that in, you get A m squared EMX plus B MEMX plus C EMX equals 0. Yeah, so then you get A m squared plus BM plus C equals 0. What kind of equation is that? It's not differential anymore. No, it's no longer a DE, right? It's awesome. It's freaking polynomial. It's awesome. Quadratic, right? How would you solve it? You try to factor, I love it. If I gave you what the numbers A, B, and C are, I'd hope to God you try to factor it first, instead of just going for quadratic formula every damn time. Right? Good Lord, I don't want to do that shit. But yeah, if it doesn't factor, then obviously you could use quadratic formula. I love it. So what are the cases related to quadratic formula? Because those cases might relate to different outcomes here. So what's the most important part of the quadratic formula in terms of types of solutions?
Like 0, 1, or
0, negative, or
All right, complex. Sometimes there will be complex answers. Sometimes there will be complex. Sometimes there will be
real number.
real. Too real, too complex, but sometimes there will be
1, y is equal to 0.
one real, right? So if you think about, if you graph this sucker, it's going to be a parabola. What can a parabola do? It could either not hit the x-axis as far as we can tell, because we don't see the whole graph. It hits it in the complex somehow. So you get complex solution. It starts up here and it just never hits. Or it can hit it once because it's sitting on it. There's your one real solution. Or of course you can go down through and you have two solutions. This is old school shit, right? I like it. But that relates to b squared minus 4ac. I mean, if that sucker is 0, you're going to get one answer because the plus or minus is sitting on that piece. If it's negative, you're going to get complex answers. If it's positive, you're going to get real answers. Okay. So let's investigate those cases a bit. Let me at least do a couple of them, and I'm going to give you this little handout that kind of summarizes some of this. All right. Let's try this process directly on a problem. Let's see what happens here. Let me give you this problem here. Now, if I did solve this, what's the quadratic formula again? It goes, okay, good, thank God. I'm glad nobody started negative b. X equals, but of course in this case it's going to be m equals. And do you notice when you get the values of m, did you get the answers? What do the answers look like? They look like e to the mx, right? So if I know what m's are, I know what the answers are. If I find the values of m, I find out the answers to this differential equation. So let's try this one out. Now, I purposefully made this nifty. I'm hoping you guys can realize the same damn thing's going to happen every time. So there's a really cool, it's called an auxiliary, let's see if I can remember how to spell it. Can't say it. Auxiliary equation. Call it the Aux equation. Can you guys see what it would look like? It's the auxiliary equation for this would be this guy. So what's it look like for this guy? It's almost too nice to believe, and this is exactly what I said last time. I said the solutions look like they came from the polynomial analog of this.
m squared minus
Yeah, m squared.
minus 7m
Yeah, m squared minus 7m plus 12. So that is the auxiliary equation. If you actually did let y equal e to the mx, all the same shit would happen. So why would you do that every single time? That's kind of like our starting place now. We go, okay, we're going to do the same thing. I'm going to get there. Can you factor that? Yeah, m minus 4 minus 3. So you get m is 4 and 3. And we remember what's in the background of this is that we're assuming y equals e to the mx. So what would that general solution look like? What would that, with all the constants thrown in? What do I get? What I got the values of m. So what's one solution look like?
4x.
E to the 4x. Right? Because we're assuming this is the answer, and what's the answer really need to be fully formed? The value of freaking m. Once I know m, I know what the answers are. So I get y equals c1 e to the 4x plus c2 e to the 3x. Schwa.
Y is it plus?
Say again?
Y is it plus?
Why is which one plus?
C1. Why do we add the two solutions?
Because remember, when we find separate solutions, we can put them together, because what does each solution do when you plug it in? each solution separately makes the DE 0. So I can plug both of them in at the same time, and it's going to make it 0. It's the beautiful thing about homogeneous, the solutions get out of each other's way. Okay. This almost feels too good to believe. It should. Yes?
Those are two specific solutions for that differential equation.
Yes. Now again, what order is this DE? Second, right? And it's linear. The functional coefficients, they're not even functional, they're all continuous. Therefore, I know there's a unique solution that exists. And I know there's going to be two solutions because this is second order DE. So did we find all of the solutions? Yes, I love it. Okay, I like it. So let's look at one more case. So this is beautiful. This is a case that you get two distinct real solutions. If that is true, you love life because you just got to throw those in front of the x and the exponential. You're done. All right. I like it. So, what about, let's see. Oh, yeah. So what happens with this one? So once you trust this process, you should be able to jump right into the auxiliary equation, even if you can't pronounce it.